Okay. Well, thanks, Joaquin. That was a very kind introduction. I'm going to start with, as Joaquin said, I have very broad interests. I'm pretty sure so far everybody that I've talked to, I've been like, oh, I'm super interested in everything you're doing and I have some ideas, so let's talk, can we collaborate? So that is usually what happens. Some of the topics, though, that I'm not going to talk about, but that Joaquin was referring to because I mentioned some of these to him, are things that I'm working on now. And I guess I would say that I'm old enough now that I feel like, it's okay if I work on things that, are a little crazy. Maybe that's what I'm supposed to do. So one of the things that I'm working on is something called the Breakthrough Starshot project, which is a plan to send the first interstellar probes to nearby star systems and send back images of the planets around those star systems. And that's pretty hard to do, especially within a human lifetime. So there's lots of challenges, and that's how I got into optical. Well, not exactly how, but that's one of the areas where optical communications and other communications are relevant. And then that's led me to also doing metamaterials, things I'm not going to talk about, and zero index materials. And so if you're interested in any of these things, then I'm happy to talk to you about them more. I was just talking to Jeff about single photon detection, 10 gigahertz single photon detectors for axion searches and things like that. But anyway, this is more of an astronomy talk. So again, I'll start with the big picture, and that is that I'm going to be talking about detecting light and what we can do when we detect light. And so I have an introduction part. As I was telling Jeff, a third of this talk is an introduction, kind of just to make sure that students know, what I'm going to talk about and what the detectors are used for. A third is on, the detector stuff. A third is on instruments, and then another third is on some science. And I realize that that's more than one. So in terms of detecting, in terms of doing astronomy, nowadays we're in a different regime where you can do astronomy with things other than photons, but I'm going to stick to photons for this talk, even though I'm interested in those other things too. And where I started was looking at, most of the photons in the universe, which are from the cosmic microwave background. And so, that's certainly one of the areas where I did a lot of work on developing detectors. I'm not going to focus on that really in this talk, but that's another thing I'm happy to talk to people about. I'm also not, at the end, I'm going to talk a little bit about these photons, which are the sort of optical photons that are emitted mostly by stars that come from, that are basically conversion of gravitational collapse into, from early anisotropies in the universe into photons. It turns out these photons in the ultraviolet part are the ones that have reionized the universe, and that's of course possible, even though there's very few of them compared to the CMB photons. There's also very few protons and electrons compared to the number of CMB photons. And so you don't need very many high-energy photons to ionize all of your protons and electrons. And so that's what these photons do. They're what you see with optical and near-infrared instruments like JWST, Euclid. These are sort of forward-looking kind of instruments. And then I guess what I'll mostly be talking about in this talk are looking at these far-infrared photons. And I mean, that's relevant for a lot of you who are working at least with, say, Joaquin and Jeff on some of the projects here, the balloon projects, or the SPT. These are the photons that are coming from, so I'll say where they're coming from. So why, this is my background, why do we want to look at these far-infrared sub-millimeter photons? And the reason is that about half, as you saw from the previous slide, about half of the photons that are emitted by stars, or half of the energy, because that was in an energy unit, it's not photons, are absorbed by the material, the baryonic material that is not stars, that's dust and gas, which heats up the dust and gas and then it re-emits. And so I have a bunch of pictures because, I realized my whole career when I was working on CMB, all we would show is images of the CMB, and it just looks kind of like a big sort of modeled like screen of, somebody put down some paint and there's blobs here and there. But if you're actually doing, real astronomy, you have some pretty pictures. Here's some pretty pictures right here. And one of the things I want to say is that it's only really been, in the last 10 or 15 years that we've actually gotten really pretty pictures in the far infrared. When I was a grad student and, a young faculty or whatever, we still were looking at blobs or, point sources and things. And so here's an example of the Hubble image of, a star-forming region in our galaxy. It's the Eagle Nebula, I think. I'll show it again. And then you can see the HERSCHEL image, which is of the same region where it's bright is the emission from the dust, whereas in the Hubble it's the dust that's looking like smoke, which it is, and absorbing the starlight. Here's another one, a composite from HERSCHEL, the Andromeda Galaxy. You got the optical image. They said I could press a button. There's the optical image over there. And here's the HERSCHEL image in the far infrared. And what you can really see nicely here is that the dust lanes, which are dark in this one, are what you see as bright in the far infrared. And so what that means is that where you see these dark dust lanes, you might by eye interpret that as, oh, there's no stars there, and that's why it's dark. But that's actually not true. That's what is there is there's a lot of stars being formed and producing this dust or smoke and obscuring the light from the stars, but glowing in the far infrared. And this is why the two are complementary, so that you can see the whole picture. Another picture example of all this is a famous one. The antennae galaxies is, I think, another Hubble image. And here you can really see sort of all this dark dust, on the large scales. I mean, you can see it if you go out at night in Arizona, where it's really dark and you see the dust lanes in our own galaxy. You see these big things. This is now showing something like that, but in these external galaxies. And it's very pretty, which is also, a nice advantage. So I'm just going to show a couple more images like this just to bring this point home about, why we study the far infrared, and also bring in some, other people that we know. So this is an optical image of this Eagle Nebula, which also I think the pink is H-alpha emission. And this is from a balloon-borne instrument called the BIT, B-I-T, the whatever it stands for, balloon-borne imaging telescope or something like that, which is a project that was led at least by Bill Jones, who's a professor at Princeton, that also worked on some instrument that I think people here, also were associated with. Oh, a balloon instrument. Wait, what's going on? Oh, good. Oh, I see. It's being zoomed. That's what happened. We're zooming it. Anyway, I show this, and why is it tilted at this angle? That's because I wanted to overlay, that with this, which I also tilted at some angle. I don't know why I tilted these at these angles, but anyway, just to make it a little bit more interesting. And so this is the, you can fade in and out. And basically what you can see is in the far infrared, you don't really see any stars, right, per se, other than a few, bright points here, which are really sort of bright protostar regions where you have stars that have just been formed and are heating up, a region around them. But what you do see are, is all the dust lanes and everything. And again, where you have dust is where, the optical light is obscured. This is another pretty picture. And again, I've gone back to this because when I was a kid, I used to like looking at the Rosette Nebula in my, backyard or whatever. So this is the Rosette Nebula. This is a Herschel image of a part of the Rosette Nebula. And again, I think this is really nice. Images are really great in just conveying things that are hard to necessarily, you can write in a paper, but it's kind of boring. But one of the things you can see is that there are these little balls like this that seem to be, have like these, smoke tails or something, right? So what's happening there is that stars are forming at the edges of molecular clouds. And as they form, they give off this dust and radiation and other stuff. And since there's a gradient in the material density around them, the pressure from the light and the other material they're giving off pushes them out of the cloud and fires them out, and you get this kind of bullet-like feature. And you can read about that in papers, but it's much easier to just see it if you have an image like this. And then again, if you look and compare with the optical, and again, this is the H alpha in pink. I like to point out this sort of thing, which is kind of like a little Joker's hat or something. Like up there, you can see it's a dark, dust cloud, and then it's filled in with the far infrared emission if you do that comparison. Okay, so that's a little nice, imaging background. So in terms of what we can learn by looking at these images and making these measurements, both at millimeter and far infrared, there are sort of three main areas, I guess, that I divide up the science into. For millimeter wave observations, as I pointed out at the beginning, the main source of light, the main photons are cosmic microwave background. So obviously, a large amount of our time should be spent studying those photons because there's so many of them. Plus, they can tell us a lot about the early universe. And so one of the projects that I'm working on is Simons Observatory. I'm not going to talk more about that in this talk. It's a set of telescopes being built in Chile to do a large survey of, the CMB over, a very large fraction of the sky down to depths that are deep enough in polarization sensitivity to really push to the next level of exploring early universe physics. Another area that you can study, as I was just talking about with the star formation, is looking at star forming regions in our own galaxy and studying the properties of those. Again, with polarization, you can also add on information about magnetic fields, and so we have a project called BLAST, which was a balloon polarimeter that flew. It's had several flights. The last one, unfortunately, we had a problem and came down only after 8 hours or so up at float. So we're hoping that we can get that approved to fly, rebuild and fly again. And then you can also do some of this from the ground. So I'll talk a little bit about that. But then mostly what I'll talk about are, doing now large surveys, but where you add spectroscopic information so that you can study the evolution of galaxies throughout, the universe. So this is, the ubiquitous sort of history of the universe, a version of the history of the universe graph where you have the early universe over there, the cosmic microwave background. So the universe becomes transparent once the cosmic microwave background photons, once the hydrogen gas becomes neutral. So the neutral hydrogen allows light to go through unless it's at a particular wavelength corresponding to a transition. And then it's neutral all the way up until reionization, as I said, when the gravitational collapse makes for stars, which produce enough ultraviolet photons to ionize the rest of the hydrogen. I like to throw in little pieces of information. The reason why there's so many cosmic microwave background photons compared to protons and electrons is, everybody knows this, I'm sure, because the cosmic microwave background photons, which we see today, were generated by the annihilation of matter and antimatter in the early universe, and that's why there's so many of them and so little of the rest of matter and stuff compared to them. It's 10 to the 9 or so photons for every hydrogen, or every proton, or every electron. I'm sure you all knew that. If you didn't know that, you can write it down and remember, and then that's a nice thing. Anyway, so that's why, as I said, there's 10 to the 9 cosmic microwave background photons for every proton, and therefore you only need 1 in 10 to the 9 UV photons compared to the total number in the cosmic microwave background to ionize all of those protons and electrons, and those are generated here at reionization. And then that's also at the time as the first stars, and so galaxies. And then from here on, you've got, all the galaxies evolving and doing all their thing and forming stars. And so the history of star formation you can plot in a graph like this, where you say, okay, well, what is the redshift down here, or the look back time, and then what is the star formation rate in I haven't put the units, but and one thing that's interesting I want to point out is two things. One, there's a lot less star formation going on today than was going on at, say, a redshift of 1 or 2. And so now people often talk about redshift of 1 or 2 as like cosmic noon. That's when, all the stars were forming. Now we're sort of in the afternoon or twilight or something like that of the history, at least, of gravitational formation of stars, right? And then the other thing I want to point out is that if you just add up all of the light and star formation by looking at the ultraviolet or optical, you miss out a lot. And so you need to go to the infrared or the far infrared to really measure all of the star formation that's going on. And the reason is just what I showed before, is that the dust, which is actually produced when you have a lot of star formation going on, is absorbing this starlight. And there's more dust when you have more star formation, so there's more dust at redshifts 1, 2, and 3 than there is today in galaxies, okay? And this is something that we've confirmed and other people have measured. So, to summarize, part 1, 1/3, which is actually not bad. We have how many hours? 2 hours. So galaxies at different wavelengths, so optical, UV, starlight, it obviously becomes dimmer as you go farther away, and the redshifting of it also makes it fainter, pushes it more into the UV pushes it more into the infrared, and so you see less of it in the UV. Whereas in the far infrared, the redshift helps usually where we're looking at either the ground at millimeter wavelengths or at several hundred microns. You are on the rising slope of that first curve that I showed, which is showing the far infrared background. And so as it redshifts, it actually you get further up to the peak. And so as redshift, you go farther away at a fixed wavelength. The far infrared light doesn't go down, doesn't dim as much. Also, as I just said, there's more dust at higher redshift, And so as you go farther away, then you see more emission. So far infrared is actually pretty good if you wanted to look at evolution of galaxies. You should do both, obviously, but to some extent, there's also, that first plot was in energy, so it's 1,000 times or 100 times longer wavelength. So that means there's 100 times as many photons in the far infrared as there are in the optical for the same, galaxies. So from an information theory standpoint, there is 100 times more information in the far infrared as in the optical. And I don't want to get into, I'm a far infrared person and you're an optical person, so I got 100 times more information. But I'm just saying. Anyway, JWST, right, is like pushing in that direction. This is why JWST is more in the infrared than HST, is to look further back, in time and take advantage of, say, the redshifting of that optical light into the infrared. All right, so what kinds of things can we measure? We can measure, we basically, if we want to study the evolution on the big scale, we want to look at average properties of things. So we want to do large surveys and do power spectra and stacking analyses and measure all these averages. And I'll show a little bit about the extragalactic background, and some stacking stuff. If we have time, that's my fourth or fifth third of the talk. All right, so let's get into how do we measure all this stuff, and what kinds of instruments and technologies are required? And so, there's a long history here in the U.S. at least of developing technologies for ultimately for use on space, but first testing them either on the ground or in balloons. And then eventually flying them on satellites. And two examples I have shown here are a balloon experiment called Boomerang that was my PhD project, where we developed the first spiderweb detectors and flew them on this balloon. Ultimately, those detectors, modified in part by Bill Jones, who we mentioned earlier, were then flown on the PLANCK CMB satellite, which was a ESA-NASA collaboration. Similarly, I mentioned the BLAST balloon telescope, which flew similar detectors, but actually not. These were now made in developed to be made on a wafer, whereas the first spiderweb bolometers were individually mounted. And so these were sort of the first arrays of those detectors, and then those were modified slightly and flown on the ESA-NASA HERSCHEL satellite, both of which were launched in one big rocket to L2 in a little over a decade ago. I also mentioned that when I was a student or a young faculty, then this is the kind of image that we had of the far infrared. This is, around the year 2000. Some of you might not have been born then, but the Hubble Deep Field we imaged with an instrument called SCUBA, and this is what it looked like, and it's not at all as pretty as the Herschel images I were showing earlier, like this one. And so why is that? And so one of the reasons is because the SCUBA instrument, which was one of the first instruments to have an array of detectors, its detectors were not really as good. There were like 37 at the most detectors or something in that array. And so these are a picture of some of the first detectors that I worked on that were used on instruments like Herschel and Planck, but also individually, used on other instruments, including ground-based instruments, balloon-borne instruments, etc. In fact, these detectors were used on, a whole bunch of instruments, mostly measuring cosmic microwave background, but also, like I said, also like Herschel on millimeter wave measurements on the ground, measuring things like star formation. And these detectors, if you look at them, they look reasonable. But if you look closely, this is one of the first ones. This is a micro-machined membrane of silicon nitride, which has got holes etched in it. And that was all made in a clean room, but that was really the first time anybody had made one of these types of detectors at all, any part of it in a clean room. If you look closely, you will see this square thing here with these wires. So this was actually a chip of germanium that was doped, so it had a particular resistance, that we would glue onto this membrane in the middle. There was a little diamond for it on the middle with I don't know if you know, there's an epoxy Emerson, I can't remember the name of it, but it was like blue and yellow, and you mixed it together. And we would take a wooden stick and carve it into a nice sharp point, and take the epoxy and glue it with by hand, and then before you did that, I would solder by hand these two wires, which are superconducting, but with copper cladding on the ends, to the chip, and then glue all of that. Yeah.
So this was the first of its kind. How did would you just put it up in a balloon and hope that it worked?
No, we tested them in the lab. Yeah. So we built them, and I mean the very first ones of these I made by hand with carbon fiber, where I took carbon fiber. I took a saw and I made a grid in a aluminum piece. Laid the carbon fiber in there in a grid pattern. Put glue on the interfaces so that it would make a mesh, and then glued one of these things on it, and then cooled it down and shined light on it, and it absorbed pretty well. So that was before graphene, I guess, but. Anyway, so yeah, we would make these, test them in the lab, shine light, measure their sensitivity in the lab, and then change them and develop them. And these were indium bump bonded here. This is an array. This is for the Bolocam instrument. This is an array of 144 detectors. So, over the course of several years, we got better at this. But this is just showing previous, what they used to look like was, it was whole thing made by hand. You take a sapphire or silicon substrate, put some metal on it, deposit it, and then string it with nylon strings, and then solder to that. And this was, this was the state of the art when I started grad school. Just, Okay, I guess I'm pretty old, so that's a while ago. But anyway, so the way these work is it's just a bolometer. You have an absorber here that's weakly coupled to your base temperature, your bath. Light comes in, and you have a thermometer. That's that chip that, you know, heats up and measures the temperature, and you read it out. It's very simple, like holding your hand up in the sun. You feel the sun's warmth, you know, on your hand. You're detecting light from the sun, right? This is how this works. And then we also, so around that time when I was still in grad school, we went from, you know, thinking about these chip thermometers, which were very reliable but kind of a pain to use, to could we deposit thin film thermometers, and we used superconducting thermometers. Anyway, this TES, this is still sort of the microwave, the micro mesh spiderweb bolometer with TESs are still used to this day in instruments that are on the sky. And this all was happening around the early, you know, 2000s. So just another sort of history kind of thing, the 1980s to 90s, I know it's a long time ago, you had these single pixel systems, and then first, you know, multi-pixel things, which like Scuba or whatever, or Boomerang had like 10 pixels. This was like the state of the art when I was in grad school. Bolocam here, 144. And then HERSCHEL and PLANCK, which were flying these technologies. But then, since then, we've gone to these TESs, where here's an example. This is one of the first ACT arrays of TES detectors. ACT and SPT have, you know, more than now 3,000. So now we're moving up, you know, into the thousands of pixels, and Scuba 2 had 10,000. And all of these are still, you know, the sensitivity is designed and is basically sensitive to or close to the photon noise limit. So we're just increasing the number. So what is the technology? Where are we now? Where are we going? Well, so one of the things that I guess when I went to Cardiff, I said, when I went there, I said, I think what we need is more of a CCD style, you know, detector technology, where we have a multiplexing built in, and we can just, you know, make everything on a single chip. And I said, we could probably do this with superconducting devices. And then, then there was this idea that originated, I guess, at Caltech with Jonas Miedzinis and Peter Day and people there, for these superconducting detectors called kinetic inductance detectors, which I'll talk about. And these are really, you know, developing rapidly now, and a lot more groups are using them, and so I'll talk about that. Also, technology is moving both in the optical and far infrared towards larger telescopes, or, you know, just more survey speed, mapping speed, right? So more telescopes looking to cover, you know, more of the sky more quickly or deeply. And then I guess the other two things I'll mention are developing and making compact on-chip spectrometers. I know there's been some work here, and there's been some work at other places to do this, so that you can make, you know, just like you have in the optical integrated field units, where you are measuring a three-dimensional, you know, cube, so you get data on images, but you also get all the spectral information at the same time. And so that's also happening, and that's another sort of multiplication by another factor of 1,000. But it relies on the ability to read out and make thousands or millions of detectors, right? If you really want to take advantage of this, and you can fuel a huge increase in the amount of information we get. And finally, there's also important work being done on metamaterials, so optics, filters, lenses, etc., wave plates and polarizers. These are also enabling technologies. But I'm going to talk about kinetic inductance devices. So what is kinetic inductance? What are kinetic inductance devices? And how can they make us be able to make megapixel arrays for far infrared and optical too? We already have megapixel or more arrays in the optical, but these will be special anyway, so we could use them there. So as Joaquin pointed out, one of the keys here is to make a megapixel array that's cooled, cryogenically cooled, or even that's not. You do not want to have a single wire or two wires per detector, because then you've got millions of wires. So the key to making and reading out a megapixel array is being able to multiplex and read out as many detectors as possible on, you know, a single readout wire. And so this is where kinetic inductance detectors are really sort of ideally suited. And I'll explain why. But before I explain why, let me just say something about kinetic inductance and then about superconductivity. So kinetic inductance, I will explain what that is, but it's a property of things where you basically have a relatively small number of charge carriers which have very relatively low or very low resistance or resistivity. Okay, and so you can think of it, and I'll get to this in a minute more, as if you are, say, trying to carry an amp of current, and you have 5 electrons, if they're just going in free space, there's nothing impeding them. You can accelerate them, and really fast. And if you make them go fast enough, well, if you have 5 electrons per some length or whatever, you may get an amp of current, right? But they have to be going really, really, really fast. But if you had 5 million electrons, you could get an amp of current by 5 million electrons per volume, per density in your whatever how you're flowing them. You could get an amp of current with them going 1 million squared times slower 1 million times slower. And the kinetic energy of the electrons, though, is proportional to the velocity squared times the number of electrons. So 5 electrons going 1 million times faster is 5 times 1 million squared energy. 5 million electrons going 1 million times slower is 5 million. If they're going 1, right? So 5 times 1 million squared. So the fewer electrons you have, the more kinetic energy they have to carry the same current. That's what I'm saying. And I'll repeat that again, but kinetic inductance is the inertia of current due to kinetic energy of the charge carriers. The other form of inertia of current that you have is the fact that when you have a current, there's a magnetic field associated with it. And that's the normal kind of inductance that we think about, which is when you're basically an inductor is a bucket and you're pouring energy into it, right? And the energy in the inductance bucket is usually going into a magnetic field density energy. But for kinetic inductance, the energy is going into kinetic energy. Anyway, there's a bunch of devices that use this kinetic inductance. They're all superconducting devices because superconductors have charge carriers that have zero resistance, but there actually aren't that many of them. And the number can change. And then there's other devices called two-dimensional electron gas or other semiconductor-based devices that are devices that have electrons that are in very, very clean environments so that they have very, very little scattering, and they can basically, regular electrons, but can go have very low resistance per electron. And those also can be dominated by kinetic inductance. So as I just said, what is kinetic inductance? Well, if you just run through a simple model, which starts with our old friend F equals ma, the Drude model of conduction in solids, then you can find a conductivity, which is just given by this sort of DC conductivity, and then there's a time constant which is related to the scattering time. And you can compute a resistivity. This resistivity then is equal to a DC resistivity plus this imaginary term here turns into an imaginary reactance, and you can write that as a frequency times a kinetic inductance. And the normal resistivity also then, if you write it in terms of the conductivity, is just given by this. And so you can calculate the kinetic inductance here is just equal to, in any material really, is equal to the effective mass of your charge carriers divided by, as I said before, the density of your charge carriers. So that's what this N is. It's the number density, how many charge carriers you have per cubic centimeter, and then times the charge of the charge carriers. So again, how does that work? Well, so basically what you're trying to do is make a current, and if you have a current going through a wire or an area, a cross-sectional area A, you generate a current. The current is equal to the cross-sectional area times this volume density, how many charge carriers you have per cubic meter, times the charge on each charge carrier times their velocity. So the current is proportional to velocity to the first power, but the kinetic energy is proportional to velocity to the second power times the number density, right, times the mass. And so therefore, for the same current, if you have fewer charge carriers, you have higher kinetic energy for the same current. That's really what I'm saying. Inductance, normal inductance, well, any inductance is related to the stored energy in a current, whether that stored energy is in, so 1/2 Li squared is the stored energy in an inductor, whether that energy is in so if you just take I and you plug it in, this I, you plug it in, there's a V squared, so that's the kinetic part. But then there's another part to the inductance, which is the geometric part, right? And that's also proportional to 1/2 Li squared, because the magnetic field energy is proportional to the magnetic field squared. Magnetic field is proportional to the current, and so the magnetic field energy stored, B squared, is proportional to I squared as well. So there's two L's, is what I'm saying. There's a magnetic L and there's a kinetic L. The kinetic L is the V squared, the magnetic L is the B squared, both of which are proportional to I squared. Okay. Other properties of superconductors. Zero DC resistance. So this is, in a normal metal, you also have kinetic inductance, but you don't see it because the DC resistance is so large that the kinetic inductance is very small, unless you are operating at a high enough frequency, which is also called the plasma frequency in a metal, where, the kinetic inductance starts to dominate. And this is why aluminum is not a good thing to use for an X-ray, telescope, or even a UV telescope, because the electrons in the aluminum cannot keep up with the ultraviolet electromagnetic fields that are oscillating around like crazy. And that's because they have this kinetic inductance. So you can see it in normal metals, but usually you don't. There's also expels the magnetic field, Meissner effect. There's a critical field and a current, and then there's a modified density of states. There's all these fun things which you need to know if you're going to calculate, what's going to happen with my kinetic inductance. But you can go and look that up. In practice, in a superconductor, different from a normal metal, so the model I showed before was the conductivity of a normal metal with the Drude model has kinetic inductance, but it also has this normal resistance part. For a superconductor, the idea is that you actually have a normal metal part, the non-superconducting charges called quasi-particles, and you have a superconducting part. And so there's this thing called the two-fluid model, where your current is carried. If I have an electric field that's accelerating charges in a superconductor, it's accelerating my superconducting things, which are these Cooper pairs, and it's also accelerating the non-superconducting charges, right? And those are happening in parallel. So some of my current is carried by my superconducting charges, and some is carried by the non-superconducting charges. Anyway, this is the two-fluid model. The superconducting charges have no resistivity, so their conductivity is pure imaginary, and the non-superconducting ones are Drude-like. And so if you combine all these things together, what you get is a conductivity or an impedance, surface impedance for your film, which has these components, which are a resistive part that is dominated or predominantly from the non-superconducting electrons, where you get some loss. Then there's two imaginary parts, a magnetic field one, which you just add on, that's just storing energy in the magnetic field, and then your kinetic inductance, which is given by this, which is basically just what I said. It's the same formula as before for the Drude model, but now it's got 2E for the Cooper pairs and whatever, and 2M, so those cancel, but that's fine. Anyway, so that's the two-fluid model. There's your real and imaginary parts. And so what we do with this, what do we use this for? And the interesting thing is you need to know that there's two parts. Why do you need to know that there's two parts? You need to know that there's two parts because the inductance depends on how many particles, what is the ratio of the superconducting electrons to the non-superconducting electrons. And that's what we're going to use because we're going to absorb light in our superconductor, just like you do in a semiconductor where you have an electron-hole pair, there's a band gap or whatever. So there's a similar thing in a superconductor. It takes a certain amount of energy, but it's 1,000 times less energy in a superconductor than in a semiconductor to break apart Cooper pairs and turn them into these normal electrons. And when you break those apart, you change the density. That changes the kinetic inductance in the superconductor. And that's what we're going to use. And why is that useful, and how do we use it? So we use it by putting a device that absorbs light in a superconducting resonator, an LC resonator. So what's a resonator? A resonator is something that resonates at a frequency. You ding it, and it vibrates like this. And you hear a tone if it's an audio resonator, or if it's an electromagnetic, you get a certain frequency out. And then if you shine light on it, what happens is the superconducting electrons fall apart and turn into normal ones, and the resonant frequency shifts. Okay, so light causes a shift in the resonant frequency. And we had a seminar speaker from quantum science come to ASU, and she said that there was a quote from somebody that said, any measurement that you can turn into the measurement of a resonant frequency of some high Q resonator, you should do it. All right, and that's what we've done. We've turned the measurement of light, how much light am I receiving, into the measurement of the resonant frequency of a high quality factor, a very sharp superconducting resonator. Now, not only is that good because it's a very thing that's very easy to measure precisely. A nice resonant cavity is a nice thing that you can measure its frequency. The other thing that's good about it is that then you can make thousands of resonators, each with a different resonant frequency. And then you can read them all out at the same time on the same electromagnetic feed line, because they're not interfering with each other, because each one is operating at its own resonant frequency. So this is what we do. You have superconducting LC resonators. Photons break Cooper pairs, change the kinetic inductance, producing a frequency shift. And then you put all of these on a line, and you read them all out with one cable, one in, one out coaxial cable. And you can multiplex, thousands of these, and they're very high sensitivity. And you can, the initial things that we made, people make somewhat fancier ones now, but they were one layer. You deposit a single layer of metal on a substrate, you pattern it, etch it, and you're done. And you have your multiplexing and your entire detector array, which is very different from either hand building, detectors with glue, or doing other types of detector fab. So this was great. And this is just showing here what happens. This is a plot of the resonant feature. If you scan through it in frequency, what happens, and you see in the way that it couples to the line, it reflects all the signal on resonance, and then it transmits it off resonance. And when you shine light on it, the resonance shifts and also changes the loss, so it gets less deep. But it can still stay pretty deep. And this is just showing a schematic of the multiplexing. You just have lots of them multiplexed on one line, and each one is at a different frequency. And so you read these out with lots of different frequency tones. And then you just monitor the phase and amplitude shifts of each tone, and that's a way of monitoring the resonant frequencies. So it's a great thing. And so we made, I guess our contribution, one of them was to design, so the initial resonators were just like the tuning fork. They were just sort of lengths of electromagnetic line that would resonate at some frequency. And we said, you can actually just make an inductor and a capacitor, like something like that thing, and then that looks like a pixel. And if you shine light on it, it'll just absorb it directly. And we called this a lumped element kinetic inductance detector, because everything is smaller than the wavelength that we're reading it out on. And so this is just where you do the single layer deposition, and you can fabricate lots of these. And this is a solution for you can make field arrays, but then there's lots of other things that you can do, making fancier things. So one of the things that we did is said, okay, well let's now couple it to a waveguide that is, circular, has two polarizations, but it's all a single mode. And so now we can make our absorbers just, lines instead of, filling an area. And you make a polarization sensitive detector, which is now two resonators, but each one is only absorbing one polarization of the light that you're shining on it. And so that's what has been used on some of these instruments. And that's the resonator right there. And the inductor you see these capacitors are really big because we push down to low frequencies. So we put those resonators on this instrument, this telescope called BLAST in Antarctica. It's red, not blue, like Illinois. But This is it being integrated in the high bay. There's Antarctica in the background, and there's just, I'm just going to go through pictures of things. So there's the telescope. These are the arrays that were used on that, and you can see they are really pretty much just silicon with a single layer, and then a couple of bond pads to read them out. Yes. Press the button. Press the button.
Yeah, was that the Kool-Aid Man on?
Yeah.
Oh my God.
That was the Kool-Aid Man.
It's pretty cool.
So this is what it looks like if you scan through, one of these lines that has like 600 or 1,000 resonators. Each one of those little lines is a different detector that you can read out with a different frequency. This is a picture of some of the readout electronics that we use. So we use readout electronics. We use FPGA-based readout electronics. I think Adrian Sinclair, who you see in that picture, has been here to give a talk on the readout electronics, so I'm not going to talk more about it. Just that I keep getting email because this readout electronics apparently also can be used for other things like electronic warfare. So I get emails saying, hey, since you're interested in electronic warfare, how about our new product, right? And I'm like, great, that's really cool. But I've never done electronic warfare. Well, not a lot. Anyway, that's mounting the electronics. All right, so last 5 minutes, I'm just going to show a couple of pictures of instruments that we are also putting these detectors into. This is a telescope in Mexico called the Large Millimeter Wave Telescope. It's a 50-meter diameter telescope, and it's designed to be used in the millimeter, so up from about 30 gigahertz to sort of 300, 350 gigahertz. I've been there a bunch of times. It's at 15,000 feet. It's the largest scientific project in the history of Mexico, going all the way back to the Aztecs. They built telescopes too, but they were less expensive than this one. So we have 3 arrays in this, just like we did in BLAST, but at millimeter wavelengths. And so these have about 10,000 detectors. They were made at NIST. This is a drawing of how the optics come in. So we designed all these re-imaging optics, and then there's cryogenic optics. The actual instrument, it's not yellow. You'll see it's aluminum, vacuum, but you'll see the size in a minute. It's pretty big. This is sort of the picture of the inside. So there you see it with aluminum. That's the window there with people, so you get an idea of the size. This is the inside, the optics, going through. It's a 3-band split by dichroic beam splitters, and there's a long story about those that I can tell if anybody's interested. This is the actual inside of the cryogenic optics bench, which a lot of this was designed and built at ASU. And this is for scale, again, so you can see how big this all is with people. The input, we were very careful to reduce stray light and have black input, stuff at the input. This is a picture of the Toltec detector array. It's really beautiful and very simple. Again, single kind of layer. And then this actually has 7 networks, so 14 wires reading out 4,000 detectors, basically. So that's a nice thing, and it goes in this assembly. This is a picture of it all put together. And I just want to show that this is working. So here are beam maps, and full width half max is on the sky. And the obvious thing you'll notice is that there's 2 arrays, there's 2 chains missing, right? So we had, you cool something down, not everything works. But out of 14, so we had 12 of 14 working the first time we cooled it down. We fixed those. This is, looking at it on the sky. There's the atmosphere, and then there it goes through. And then if you remove the atmosphere, then this is a scan through a point source. And this is the Crab Nebula in 22 minutes with at 1 millimeter.
Was the atmosphere slide, was that simulation or data?
This is data. All right. And so we're doing surveys. So we've been commissioning this. I will say there was a fire on the mountain that cut out the optical fiber link, but that's been restored. And then over the summer, it's storm season, there was a lightning strike which knocked out a generator. And so we're waiting for a transformer. But it's also summer is not the observing season, so we're going to get going again in a few more weeks. on the fall season. We haven't started yet, but we're going to start. There's 10 100-hour surveys planned, and surveys have been defined. So 4 of them are shown here. And I just want to, I want to end with one last thing, which is an example of some science that you can do with Toltec or other surveys, because I know that this place has something to do with the dark energy survey, I think. There might be some people who've done some of that. And so I have had some students working with the dark energy survey, probably talking to some of you because they've been like overloading the server for, grabbing images, right, from the database. Jenna Moore, in case you know who that is my student. Anyway, so we've been we've been taking galaxies from the dark energy survey catalog and then stacking them on millimeter waves. So looking at redshift 1, looking for energy injection from gravity and AGNs. And there's a paper that was just published last week on this with that title by my student Jeremy Meinke. And we selected these galaxies using the Dark Energy Survey catalog data and WISE colors to have redshift about 1 and low star formation rates, so to be sort of quiescent galaxies, so that supposedly they've already gone through their feedback phase. The galactic centers, which go through active galactic nucleus phase, have put out a whole bunch of energy, and that's quenched star formation. Now, it turns out when we looked at them more closely, pretty much all these galaxies have tons of dust in them. So, I'm not really sure that they're not forming stars at the moment, but, they're at redshift 1. What are they going to be doing? They're forming stars. Galaxies at redshift 1 are forming stars. Anyway, but this is their redshift distribution. And so we stacked, on order 100,000 of these galaxies from DES on ACT and SPT. And here you see the ACT one on the bottom, SPT, and they, agree. You can't see it that well, but one of the main things we see is dust. So that's the first thing. There's a lot of dust. The other weird thing is the dust is extended. It's not like a point source, which is like, what's going on there? So lots of scratchy head things when you do this. But we also see the SZ. So if you look at the profiles, these are the profiles at 220 gigahertz is red, so that's where you see the dust. 90 gigahertz is black, so that's where you see the SZ, the Sunyaev-Zeldovich, the hot gas absorbs the cosmic microwave background. I haven't explained that. Somebody else can explain that. And then the blue is in the middle, where you have a combination of the two. And if you plot the spectrum, you see it's a combination of this Sunyaev-Zeldovich spectrum type thing and plus dust. And these are the ACT and SPT samples. That's cool. Then if you look at the dust, it's extended and there's this long tail. It's very high signal to noise. That tail is galaxy clustering, so it's dust from other galaxies that are associated or near to these galaxies. And that was interesting. This is on scales of sort of a few arc minutes out to like 20 or 30 arc minutes, and we detect this all the way down. And so we measure the total energy injection from these galaxies, and it's like from the Sunyaev-Zeldovich effect, and it's approximately 2 times what you would expect from just gravity. So there's some evidence that the nuclei have put energy out. So they've been heating this gas around these galaxies. Most of the uncertainty, though, in this is in the halo mass. So we can break this degeneracy of halo mass and whatever with Toltec. By measuring better angular resolution, and we can detect these galaxies, pretty well. But then, in order to try and see if we could limit the halo mass, we tried stacking them with Dark Energy Survey. And so, I want everybody Dark Energy Survey to just pay attention for a minute, because this is what we got when we did a stack of like 100,000 galaxies from the DS catalog plus WISE in GRIZ, whatever Y bands. These galaxies, redshift 1. This is what we got. And we thought that was weird. Now, what did we think was weird? We didn't think the point in the middle was weird. That made sense. We didn't think that the stuff around the edge, which is like the extragalactic background, with variation, is weird. What we thought weird was that dark ring. So we stacked these same galaxies on pan-stars, and we saw the same dark ring. And so we had one theory, which we tried for a while, which was, is it dust? So we stacked some of these galaxies, the ones we could on HERSCHEL, and yes, they have tons of dust, okay? But the dust is not that big. This is 10, 12, 15 arc seconds across, right? And so we decided it's not dust. So we think we know what it is. If you are willing to talk to me afterwards, I would love to, share with you what we think it is. We also measured from these stacks, we measured the extragalactic background light from that part around the edge. And so this is what we got just from the resolved sources, which makes sense. This is a profile of those things. Again, I'm happy to talk to people about what it looks like. All right, so let me end past time, I know, but I just wanted to end here. Again, I have lots more, but this is a summary. The kinetic inductance detectors are, taking over the world, right? We're ruling things. Well, not quite. There's still a lot of experiments using TES, transition edge sensor bolometers. Those are the state of the art, certainly still in the CMB world, although I will point out that Simons Observatory, there's a UK contribution that's going to be now mounting the kinetic inductance detector instruments on that CMB experiment. But here's a list of ones that have been, not a complete list of instruments that have already used these arrays and ones that are coming soon, including ones that people here are working on. And so I will finally end there, and thank you all for staying and not, and having pizza. Even though you already got pizza, thanks for staying to the very end. So thank you.
Questions for Phil?
Wow.
Anybody?
Totally technical question. Thanks for the talk. On your list of a zillion experiments, I saw one I didn't recognize. So SOUK, ground-based polarimeter. Can you say a couple words? What's that? What bands?
That's the Simons Observatory UK
SOUK.
contribution.
I see. Okay.
Yes.
Thank you. Yeah, I was trying to pronounce it. Okay.
Yeah.
Thank you.
Okay. Anything else?
Any ideas what that dark ring is?
I think you're meeting with Robert right after.
Next? Okay. You'll tell me afterwards?
Oh, I don't know.
Aliens.
I started trying to go through things I was worried about, and I haven't come up with what it was for that, so that's good.
Okay. We think we know, so.
I would love to hear it. Give me
Why don't you tell us?
You can tell the rest of them.
Well, I was waiting for that question. It was like I'm throwing out, possible questions.
I was going to get the answer anyways.
We think.
Can you tell us where your guess is for the ring? Thank you.
So here's the test that we did that sort of gave us some indication, right? So what we did is we separated this data into, I separated the whole catalog into magnitude bins.
Sure.
And this only shows up when you start getting into so these are all magnitude 23, 24 sources. And this only starts to show up when you're like below magnitude 22 or 23. Otherwise, there's no dip. There's no dark ring. So what we thought was that if your sources that we're selecting are faint, then we're missing some of the sources that we're looking for that are this bright if they're near objects that are a lot brighter.
There's a deficit in catalogs in the exact same sense.
Yeah. Right. And we're selecting from the catalog.
It's about the right size. So that's kind of where
So right now, what Jenna is doing is making a plot. She's done a histogram because she identifies and removes all of the sources except for the middle source and has a magnitude for each one of those, right? Including ones in the catalog and not in the catalog. And then she is plotting a histogram of the magnitudes as a function of radius away from the center of this source. And so what you see, obviously, is she's normalizing that, and what we expect to see is that there are fewer bright magnitude sources near the center of this source than there are further out. And that's because if there was, I mean, obviously, if there was a bright magnitude source right on top of one of these sources, then we wouldn't see it, right? And so, have to get a certain distance away until you, from a source brighter than a certain value in order to be able to identify this source. And what that means in reverse is if you then take a sample of sources that are faint, all a certain faint, pretty faint, and you stack them all near those sources, you will have fewer bright sources than you do if you just stack random points.
So you've selected things that are isolated to do this.
Yeah. Right. Well, we haven't intentionally selected things that are isolated, but it's just happened because they're faint, and that's the only way to do it. So another way to check this is if there was a better, higher angular resolution survey or something of some subset, and we could look at that and see, okay, what if we stack on DES, those sources, then do we get a narrower thing or, whatever, right?
I don't know if you'll get a high enough number count to do the same.
No, I know. I'm waiting for that. But because of this effect, I think that people who are doing analyses for like non-Gaussianity, FNL, using the catalog and saying, oh, we're going to analyze. So then that means there's a correlation or an anti-correlation between the positions of, sources at magnitude 23 or 24 in the DES catalog and, say, nearby or bright sources, right, in the sky at a low level. And so there's a paper by the, people using DESI data where they were doing this, and they're like, oh, we get FNL as 50 or something. And I'm like, yeah, because that's the FNL of the sources that are missing.
Yeah, there's another paper, Bernstein, I think, or one of his students, that was showing that you could measure the kind of distribution of the population that we're missing, but the faint background population. You can see it in our background samples.
Yeah.
So.
Yeah. So if you can refer me to that paper, because we want to publish this, I guess.
Absolutely.
This is like, you look at it and you're like, wow, that's weird.
That's messed up, yeah.
So we want to publish it and then say, well, this is what we think, and then we have this histogram plot maybe, which hopefully can go with that. And yeah.
Oh, yeah, so.
All right. So just kind of more of a manufacturing question on the kids' side. So you showed the array, and you said there were 12 out of 14 of them that worked well. But you said that 2 of them were, like right there. You said like 2 of them weren't like working. So what is the kind of the process of, I guess, repairing that? Because I'm assuming you make the wafers in like a clean room.
No, it's the array is fine. This is all wiring, cables, bad cables, or a component that is failed, or a amplifier, power line that is grounded or something like that. So the arrays are super reliable and robust, and this is all us. This is all on us. This is not NIST.
Okay. And do the kids' arrays, do you guys manufacture all of that too?
Well, we have made resonators and arrays, and I certainly made some. We made some when I was in Cardiff, and they're now ramping up to make more. These ones were all made at NIST. The blast ones were all made at NIST. NIST is like a national lab. They like making large numbers of things, and we sort of like making prototypes. And then, I was having this conversation with Jeff on the way over, but yeah, back there.
Yeah, it's going back to the previous point. So, wouldn't you expect the ring to change as a function of frequency band if your theory is true?
Right. So you would, if it were dust or if it were some astrophysical thing, you would expect it to change. If it's a galaxy selection thing, then you don't. Right. You don't. You expect it to change a little bit because the galaxies that you're selecting have different colors or whatever, and it does change a little bit. But yeah, I don't know. We tried, and I was thinking this would be great if it were dust, right? Because if it's dust and it's that extended around these galaxies, we could easily resolve it with Toltec. That would be fun, right? And if it were dust, it's blocking the extragalactic background. So that's a really cool thing. It's a dark, dark measurement of, it's a dust cloud measurement of the extragalactic background. You could do it as a function of redshift, but it's not dust. Unfortunately.
And where is Toltec? Where's the footprint?
What's that?
The Toltec footprint?
Yeah, so the resolution of Toltec is 5 arc seconds.
No, the footprint.
The footprint is as big as this slide.
Like which? The survey footprint.
Right. So, sorry, the instantaneous footprint of Toltec is 4 arc minutes. So that's 4 arc minutes. The survey sizes depend on the survey. Where was the survey? Yeah, so it's at the end.
You're just wondering about the RA deck.
Yeah, 90 square degrees is one. 1 square degree and 100 square degrees are the other two, and then the fields in filaments is just targeting certain filaments. I don't know how many.
Do you know where the 100 square degree one is?
Yeah, it's actually divided up in 10 different fields of like 10 square degrees each, all of which are like cosmos and Boötes and whatever have everything else. Yeah, I mean, I would love to just focus on sort of DS field, right? But other people are like, no, you're at 19 degrees north, so you can see my field, and LMT's at 19 degrees north, so it's not super easy to see a lot of the DES field, but we can see some of it. We can overlap. I'm sure there's overlap with that, and certainly on the equatorial fields. Yeah.
Okay. Let's thank Phil again.
Yeah.